Hello everyone! In this video we will continue to examine topic 1.3, vectors and scalars, and in particular we will discuss the most challenging aspect of vectors so far, which will be adding vectors at non-right angles algebraically. Okay? Alright, so we're going to come back to a problem we've already solved graphically. That is, we want to add vector A, like this, plus vector B, and we want to do it tip to tail, okay? So as we discussed before, we could take vector A, copy vector B, add them tip to tail, and so our net vector is right here, A plus B equals C. Okay, so we already know how to do that graphically. But as it turns out, we can use trigonometry and algebra to add them and get our final vector, vector C, without pulling out a protractor and without drawing it exactly to scale. Okay, and we can do that by decomposing each of the vectors. And here's the key. In order to get vector C, you can decompose both A and B along the horizontal and vertical directions. And then by adding up the horizontal vectors, okay, from both A and B, and adding up the vertical vectors from both A and B, you can get the total vector, get the horizontal component for vector C and get the vertical component for vector C, which is all you need to get your final vector for vector C. Remember that our goal is not just to get the length of vector C. Our goal is to get the angle for vector C as well, denoted on this particular diagram by phi. So before I pull out the algebra here, okay, this is what we're doing visually. Note that A can be decomposed into the horizontal component of A and the vertical component of A. So let's focus on the horizontal component first. A is here, right? A cosine theta. Now B is also pointing a little bit to the right. And this is the horizontal component of B, B cosine phi. Okay? So if I take A cosine theta plus B cosine phi, that gives me the horizontal component of my final vector C, right? The sum of the two. So the blue part horizontally of A plus the red part horizontally of B gives me the total horizontal part of the vector I want, vector C. Notice that I can do the same thing with the vertical direction. But now vector A's vertical component points up, and it's pretty big. Vector B's vertical component points down, and it's a little smaller. So we're going to add them up, but we're going to pay attention to direction too. So I take the vertical component of vector A, that's A sine theta here, and the vertical component of vector B, that should actually be phi. So I'm going to correct that briefly. I hadn't caught that. So this is B sine phi and B cosine phi. Oops. B cosine phi here. All right, so coming back to my discussion, we're going to take the total vertical component of vector A sine theta, and add it to B sine phi, but paying attention to direction. So the B sine phi component is negative, okay? Choosing negative to be down. And so our total result is what's left over. The magnitude of A sine theta minus B sine phi is that distance right there, which is the component we need for vector C. So what is vector C? What is the x component, or the horizontal component of vector C? It's just A cosine theta plus B cosine phi. And what is the vertical component of vector C? It's A sine theta minus B sine phi, paying attention to the direction of B. And then what is our angle for vector C? Right? Notice we have the two sides, right? What is our angle for vector C? Well, that's just tan of psi for angle psi equals cy over cx, okay? And if you wanted the length, all right, you can do one more final step. If you needed it, you can take the length of your total vector C will be equal to the square root of cx squared plus cy squared. Okay, so if you were asked to specify the length of vector c, so now you have the angle of vector c, it's the arctan of cy over cx, and the total length of vector c. So try that out with this particular example here with a magnetic field vector. That's what's given.